regression is supervised learning for the continuous data, right? What is regression? We start with linear again, right? Linear regression. So most popular regression algorithm is the least squares, Try to find a line of best fit that minimize the total of square of the errors. So first we have data. Right, so now we have input x. So input. Okay. And then we have the output. So in this example, we only have one input variable, single variable. Okay, only one. So the data points, the blue dots are the data points. Okay. I think my pen is not as good as I expect. Okay. Try another one. Okay. And I should use the blue color, the data points, sample points. You can call it sample points. And then we try to find the line, this line, linear line. All right. The black one, which is which is a linear function that which we are most familiar with, right? Y is the linear equation of input x with a weight parameter to adjust the slope of the linear square and a bias to change. Here is the bias E to change the position of the linear line. And our prediction is on the line, right? Because we use this linear equation. So suppose we have input x equal to 10, right? Or x equal to 10 here. Then the prediction will be here. A prediction, right? If the input is 10, then the prediction is here. And the distance between the prediction and the real value is the error. So the distance between our prediction is on the linear equation, so it's on the black line, and the distance between the point on black line and the blue circles, our data, our errors. So our goal is to minimize all the errors, sum of the errors, right? So our goal is to minimize the sum of the errors. From arrow 1 to arrow n, and the arrow, of course, the prediction is use y prime. So the arrow is y prime minus y. Y is our answer labels, and then I is equal 1 to n. Suppose we have n points, so yi prime, right? Okay. So the linear equation can be, if we have multiple variable, we need to use vector to represent the data. So we will have a W in bold font, which represent vector. Or another way to represent vector is to use an arrow. But anyway, usually we use the line to multiply by x plus bias. Bias is just a scalar, and this one can be equal to to a vector. You can combine the bias and the weights into a single, vector and multiply by x. Multiply by vector x. X will be another vector. X1, x2. Okay, so this is mean square error. So our goal is to find a line that minimize the error. Okay. Usually we will write the mean dot. Mean dot means minimize. It's a verb, not a noun. Minimize the error. Okay, so you can see, that's and then we can solve this use a pseudo inverse function. We will talk about pseudo inverse later when we introduce linear algebra. So there's a pseudo inverse square solution. So basically, there's no division in linear algebra, right? So we can just multiply an inverse matrix to the answer. So we can solve the equation. Okay. So the equation is I can quickly review the linear algebra for how to solve this equation. So suppose we have a y prime is equal to wx. Suppose we combine the bias with the weight, and then we need to have an inverse function first. But to have inverse function, the matrix x need to be invertible. Need to be square. So we multiply both sides by the transpose of x. Right, and then we multiply both sides with the inverse of this function. This is square matrix, and then it may be invertible, have an inverse function, may not. So if we multiply by both sides with the invertible matrix with the original matrix, then this one is equal to I, which is identity matrix, which is 1, right? So we multiply to both sides. So for this part will be equal to this one, because I don't have room to write. So that's how we get the pseudo inverse. But xt multiplied by x is not guaranteed to have a unique function. If you want to have a unique function, you need to be if and only if the colors of x are linearly independent, then xtx is invertible. If it's invertible, then we can multiply both sides with the inverse function, and then remove this part. Remove this part, and then you can get this one, right? In this square. So that's for statistics. So let's see an example, simple example. This is from scikit-learn Python package. So there's a diabetes data set. We want to find what's the feature related to diabetes, right? So there are 10 features: age, sex, body mass index, BMI, average blood pressure, and the 6 blood serum. I don't know what's that. Maybe blood quality measurements. And we select only single feature to visualize, visualize the line, right? So only single feature, and what is the most relevant feature to diabetes? You guess. So it's supposed to be BMI. BMI. So BMI is very important. My BMI is a little bit high. So yeah. Anyway, so to visualize the linear square, we select BMI, and the Y is the chance of getting diabetes, I think. So we can use a linear square to predict it. And it's a small data set, has only 442 patients. Usually you can't get large medical data set. It's very hard to get medical data today because of the privacy. So for the regression, we usually normalize to all the data to mean and the square length. So usually subtract all the data by the mean. So we have a neural mean and divide data with standard deviation. So this is a linear regression, and here's the code about. So we first load the diabetes. Suppose you know Python, and then we got only one feature. So you select the axis and feature two. The last one is feature. Okay. And then just call it linear regression model and feed the data. Feed is the training in machine learning. Feed is statistics, right? So we feed the input X with using the linear model with the answer with the diabetes. Minus 20. Also here is we need to split our data set, right? So we select the last 20 patients as test data set. So we have 20 patients as test data, and don't use test data for training, right? And the rest for training. And then we feed the data. Then just one line, you can get your model. So let's test how the accuracy, then we use predict. We use the model to predict on our test data set. Okay, then this is the result. Then we plot the prediction result. Because we only use a single variable, so it's not very accurate. But however, you can still see that some data patients are fit by this simple linear regression model. So have you ever wondered why this function is called regression? It's actually like approximation using linear, right? What is regression? So I Google it on Wikipedia. So the first one that invented this terminology is a statistician. He tried to predict the height of humans, use their parents' height, right? Predict a person's height with their parents' height, and then he find out that the parents that are very tall, have higher chance to have children that have lower, slightly shorter than their parents, and the parents are very short, tend to have children that are slightly taller than their parents. So actually, the height of humans are come to the average, regress to the mean, So it's called regression, So it's not related to what we are doing. Yeah, so that's why it's called regression. Maybe personally, I think approximation is a better terminology. So in a scikit-learn algorithm cheat sheet, you can find that there are many different regression algorithms, but actually they are all based on linear regression. Let's see why. So first, linear regression has a problem that the linear regression is sensitive to outliers. So what is outliers? Outliers means that a few sample points that far away from the mean. So in this example, Yeah, where's the outlier? So suppose we have some data points, and then an outlier will be far away, like outliers, right, far away. So it's far away, very few, but their existence will change the mean dramatically. Okay. Because, for example, it's very common to have an outlier in my class. A few students never come to our classroom, right? Only like 2%. And this outlier will have a very low score and draw down the average. So the average, usually the average of my class is around 85, but the true average is around 88 or 89. So now we know the most reliable statistic to describe the average person is the median, right? So sometimes we use median to describe better than mean, right? Better than mean. So how can we solve this problem? So if we have an outlier here, the total linear equation will be shifted. However, the baseline is the original one. So this is supposed to be the best, but the red lines is affected by the outliers. So the solution is to use regularization. Regularization. Yeah, it's a long terminology, but what it means is that regularization adds small amount of bias during training to reduce the variance on test data. So in other words, it make your training process a little bit more difficult. And usually your training accuracy will be slightly lower than no regularization. However, you will get better results on test data. So let's call reduce variance on test data. Okay. Let's see an example. Okay, here's a picture I found on the internet. Regularization. So usually, here the weight is beta. Okay, the weight is beta. Let me choose a color like purple. So beta is the weight. And then we are doing linear regression. I mean, least square. If for regularization, so for those circles they have same error. They have same cost. So suppose, well, let me see. Suppose this die will have cost 1. So the whole circle will have the same cost. And the circle will have the cost maybe cost 0.5. Suppose different circle has different cost, but all the points on the circle has the same cost. If we add some regularization, we will try to add this term to our objective function. So while we are minimize, in other words, while we are trying to minimize the error, we will add some term here. So we minimize both the original least square target and also the parameters. Sorry, it's very difficult to write a beautiful lines. Let me try again. Okay, so our goal is to minimize, right? Minimize. Remember, there's a dot means this is a verb. Minimize the least square error, but regularization will add additional constraint or additional requirement, additional terms in the objective function, which it will want to reduce the L1 norm or L2 norm of the original function. So you will need to minimize the whole objective function. This term is called regularization term. Usually there are two different regularization terms. This one is use L1 if you use L1 norm. Otherwise, if you use L2 norm, then it's called the rigid regression. L1 is called the lasso. So the regularization term will draw a region here, which means, as I said, the circle on the red circle, all the points have the same cost, same y prime, same prediction, same error, and then so if we add regularization term, we will prefer this point on the circle because we will prefer the intersection between our regularization area, right? And the answer on the and the answer on the red circle. So that's it means that we try to minimize our cost while we try to minimize our weight. And why we have this picture? This picture shows that if we use L1 norm, which is absolute value of the weight, then it will look like a rectangle, right? Diamond shape. And then if we use L2 norm, then our regularization area will look like a circle, right? A circle. So L2 norm will has. So in the in this picture, you can see that the L1 norm will prefer more zeros on their data set. More zeros, right? L1 has L1 regularization term has more zero weight. More zero weights. So which means the result is more sparse vector. Yeah, you can look at this. In this point, that beta 1 equal to 0, right? And at this point, beta 2 is 0. So it will prefer that some of the parameter, some of the weights become 0, which make our vector sparse. This is a preferred feature of machine learning.